So the next part we're gonna move on to is RX and alcohol. Yay! So over here, we can see that I've decided to form 2-bromopropane here. Say so it's a follow up from 2-propane 2-ol. So I can put HBr gas, then alkene, then form this 2-bromopropane, or I can do limited Br2 UV light from an alkane to an RX. Okay, so over here, the alcohol and RX are actually you can convert one to the other and the other to the other form. So these are the different reagents and conditions that we must take note of. So from RX to alcohol, we use sodium hydroxide and heat, which is what you will find in alkaline hydrolysis for some other reactions as well. But in this case, this is called nucleophilic substitution. So over here, nucleophilic substitution, not alkaline hydrolysis. So just take note of that. And from alcohol to RX, we have actually 4 possible reagents that we can use, and they have different conditions as well. So firstly, we have PX3. So X stands for anihalogen, so it's chlorine, bromine, and iodine in this case. So when we use PX3 heat, when you use PX3, you must always have heat. So a good rule of thumb is that when you use PX3, the 3 must appear everywhere, okay? So it's 3 moles of ROH, then you have PX3 and give you 3 moles of RX, and you have H3PO2, which is your phosphoric acid. Now you have your PCl5, your ROH plus PCl5 to form the POCl3, which is the liquid, and it forms hydrogen chloride as well. If you use thionyl chloride, from ROH, from SOCl2, give you SO2, which is sulfur dioxide, RCl, and your HCl. So the good rule of thumb is that if you use anything else, like PCl5, SOCl2, besides PX3 heat, you're going to form 1 mole of each product and reagent. When you use PX3 heat, everything must be 3. There's 3 somewhere, either be in the subset or a not subset, subscript, or the molar ratio itself. The last one we have is our HX gas. So we have our HCl gas. The reagents and conditions used here are slightly different, even though I don't think it's really stated specifically. But the exact reagent conditions are as follows. So if you have ROH plus HCl, if you RCl and H2O. So just mind that whenever you HCl, you're going to produce a water molecule. We use these things above. So we use HCl for PCl5 and SOCl2. Okay, so over here, what we want to know is that because HCl, I think is hydrogen chloride, is readily available some sort, so they can just straight away use dry HCl. But do know that for HBr and HI, you need to prepare them. So the way to prepare them is that for HBr, you need sodium bromide with sulfuric acid to prepare your HBr. So the reagents and conditions are over here is corn sulfuric acid, heat, and sodium bromide. But if you want to prepare hydrogen iodide, you use sodium iodide and phosphoric acid, and then it will give you these products. And the reagents and conditions are sodium iodide, and you have your concentrated phosphoric acid. So note the acids here are concentrated. Okay, so the next part is that we're going to find out what other reactions RX can undergo. So firstly, you can undergo our nucleophilic substitution. So our bromine atom will be substituted for CN. Okay, wait. I know there's an error here. So let me just correct that, Okay, so this is what we call it as a step-up reaction, and it is very, very important that we know this, because in synthesis reactions, sometimes like our starting product has 3 carbon, for example, then my product undergoing some reactions gives me 4 carbon. So we notice is that there's an additional carbon in the product. So this is what we call a step-up reaction. Step-up reaction is when we add 1 more carbon. So for example, here I form a butane. So what's the reagent condition to firstly do a nucleophilic substitution of Br for CN is that we use ethanolic KCN, or we can use ethanolic NaCN, but we must have heat. Okay, so heat is very important. And I just realized It's not supposed to just be butane. You cannot form butane. Oops, that was a very wrong example. But okay. Okay, this is a possible product. So we form a carboxylic acid when we undergo a an acidic hydrolysis. So acidic hydrolysis is sulfuric acid aqueous heat. Or if you want to go an alkaline hydrolysis, you can use NaOH aqueous heat. So remember I said just now earlier, it's like we can convert RX to alcohol. We use NaOH aqueous heat. So that's what a nucleophilic substitution. So similarly for alkaline hydrolysis, we're going to use NaOH aqueous and we have heat. Of course the product form will be different. It will be just be O minus instead of the OH, yeah. So this is something that we can take note of. So it hydrolyzes your CN bond, breaks it, it gives you your this bond. Yeah, this product. Okay, so yeah. Okay, so yeah, what happens now is that I'm going to talk to you why why carbon is the one that will attack our why this like this electron this bond pair directed towards carbon and not nitrogen. Okay, so if you will look at the chemistry of Cn minus, right, because it's actually carbon is so it will be this 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 this. So because nitrogen being more electronegative atom, so it will pull one electron towards itself. So therefore, we have this overall negative charge, so Cn minus. So the double bond is formed between it's actually shared pair of electron, but the third one we can find is the dative covalent bond. So if you want to be more specific, you can do you can show this arrow here. Yep. So even though my nitrogen so has the negative charge, and by rule of thumb is that negative charge is like very strong. So by right, we should see that the bond pair electron on nitrogen atom should be the one attacking the carbon or that's attached to this this halogen over here. But the thing is that because nitrogen is a very electronegative atom, so its bond pair electrons are not so readily donated to C. So like imagine if I'm very electronegative, like I want to keep the electrons for myself, I'm very selfish. So what will happen is that I have my bond pair electrons on C instead that will go and attack my slightly electron deficient. So it's about the other positive. Carbon. So I'll explain the entire mechanism of nucleophilic substitution for Rx in a moment. So by this is how it happens. So we just need to take note of it, yeah. So it will be the bond pair electrons on carbon instead. So sometimes they will ask, and you just have to tell them this reason. Okay, so there's also the reduction reaction of my CN to a primary amine, so it's possible. So there are actually two ways of forming a primary amine. So we can just either we just use excess corn NH3 heat and tube, or we can just use by CN route. Okay, so the way we do this is that we have two possible reagents and conditions that we use. First is the reduction. Second is by using hydrogen gas. So the first one is reduction by using a reducing agent. So our reducing agent here is lithium aluminum hydride in dry ether, or we can use our hydrogen gas, nickel and heat, or hydrogen gas, it's a typo here, it's just hydrogen gas or platinum catalyst. So we're just still going to end up with the same product. So we're just going to use a CH3CN as a simplified representation here. So if I were to use lithium aluminum hydride in dry ether, I will make sure that I have my H atoms out. I add 4 H atoms. Then for my primary amine, for hydrogen gas, I just use H2 gas. And then I will get my primary amine as well. So it's the same reaction. Okay, so the next reaction that we'll be looking at is the reaction of Rx with our to form our primary amine. So yeah, so when we're looking at nucleophilic substitution of our halogen atom to form our from Rx to a primary amine, what we need to do here is that we need to put concentrated excess ammonia, and we have our heat. So if you want additional description, you can put excess concentrated ammonia heat in sealed tube. The one that I underline is not really crucial when it comes to stating the reagent and condition, but if you want that additional clarity, then yeah, there's no problem with that. So it's excess con ammonia heat in sealed tube. They form our primary amine. Now I'm gonna explain why we have to use excess ammonia. So imagine I have a reaction tank here. So I have a lot of ammonia and like very few Rx. So the thing is that when I have a lot of ammonia, right, my ammonia, like the lone pair of my electrons on my N atom will start to attack my electron deficient, slightly electron deficient delta positive carbon here that's attached to that have the hydrogen atom attached to it. Okay, so the thing is that because it attacks that, so electron deficient, so there's nucleophilic attack, and therefore I can form my first substituted primary amine, right? So this is the product here. Okay, but to be much more clearer, it'll be CH3NH2. So this is my product here. Okay, so now knowing this nitrogen atom, it will of course have like its lone pair electrons. But the very interesting thing about this reaction is that after reacting, right, you'll find that it doesn't retain this, NH3. No, it doesn't. What it does is that it prefers to have its lone pair of electrons with it. So therefore, it will lose the hydrogen atom and you get its lone pair electron back. Okay. So where does the hydrogen atom go? The hydrogen atom will be, as we will see later using this example, to be honest, actually the hydrogen atom will be a heterolytic fission. It'll be 1, 2, 3, 4. Yep, so because the bond pair electrons here, so heterolytic fission here, so then our Br minus will be attacking hydrogen to form my HBr. And then I will get, sorry for the mess here, it's very messy, I know. So it's a primary amine here. Yep, so that's how it works. Okay, so so if we were gonna have okay, but if you think about this, like in chemistry wise, right, like it's like this kind of reaction doesn't happen. Why? Because nitrogen is not electron deficient at all. It's not. So the way this nucleophilic substitution works is that because there's a lone pair electron, so it's gonna attack electron deficient species, right? That's how nucleophilic substitution works. So I'll be talking a bit about electrophile nucleophile in a while. Okay, so just for the additional clarity, yeah. Okay, so what happens here is that our lone pair electrons on N will be attacking the electron deficient carbon here. Ooh. Oops. Yep. So that happens, and then our bond breaks, and it gives the heterolytically, and then it gives our halogen that additional electron. There will be forming a halide ion. Yep. So if we're gonna have a lot of our Rx inside the solution instead of our ammonia, so you can see that in excess, right, then there's a higher probability of our primary amine, the lone pair electron on the nitrogen atom of the primary amine to attack another Rx, right? And then because this is also electron division, so this can go on and on. So then we have our second substitution, then this second, this is third, and then one more time we're gonna have our fourth substitution. So this will form our quaternary ammonium salts. So this is kind of similar as to how you form NH4Cl. It's kind of the same idea here. This NH4 plus and Cl minus. So instead of like the H, the 4 hydrogen atoms, this actually our four alkyl groups, they're all the same because we only use one type of it. Then yeah, so anyway, and our 4 plus CR minus something like that. This is just in general form. So yeah, don't be surprised when you see some products like this, like some complicated like you know C, they'll probably C13 and like H. I don't know how many. There's like N, H, how many N, how many H, and then there's only one N, how many H, and then there's a Cl. So it's like don't be surprised when you see this kind of like molecular formula. It's basically referring to 4 substitutions. So you form a quaternary ammonium salts. Yeah, so that's what happened. Yeah. Okay, so but the thing is that each time that you substitute, it actually reacts much more faster. Why? Because remember the idea of okay, remember the idea of electron donating alkyl groups. So these are all alkyl groups. Your methyl group is an alkyl group. It's electron donating, so it makes the lone pair of electrons on nitrogen atom more readily available. So therefore, it's much more reactive, and it's more reactive and more readily donates, attacks electron deficient carbon. Therefore, substitution occurs. Therefore, it has increasing rate of reaction as you substitute more and more. So this is an interesting concept that you should keep in mind of. Okay, so now we're going to be moving on to nucleophilic substitution as to why the whole process. I'm going to explain the whole process of why things happen and why they happen for a reason. Okay, so now when we come to nucleophilic substitution, there are actually 2 types of it. There's SN1 and SN2. So what does SN1 and SN2 means? I will be going through it now. So when they ask you to describe the mechanism, there are actually you need to state the name, right? You state the full name called nucleophilic substitution, and you have to say the type of nucleophilic substitution, be it SN1 or SN2. You must write it down. So what does SN1 SN2 mean? So S means substitution, then N means nucleophilic, and 1 means unimolecular, or 2 means bimolecular. Okay, so we can also deduce this easily by looking at the rate equation. Okay, so you remember from kinetics, right? The rate equation is based on the slow steps. So so in SN1, there are actually 2 steps to this reaction. So and it is slow and it's fast, and so since the slow step is talking about an Rx, so definitely the first step is slow step, second step will be the fast step. But in SN2, there's only one single step, so we have the reactant is just a nucleophile and an Rx, so therefore it's just the rate equation is just based on the step itself. So recall only when you're talking about a single step, then is the rate equation have the power of like the reactants that's raised is equal to the molar ratio. So that's only for a single step reaction. Otherwise, you'll be looking at a slow step for rate equation. Okay, so why do we have SN1 and SN2? Let's us look at the theory now. So there are 3 arguments to this. So there, first one is the stability of the carbocation ion. Second is the steric hindrance. Third is the electron deficient. The electron deficiency of the carbon. It's like the extent to which. Okay, so I highlighted the first argument is to support why SN1 occurs for tertiary Rx, and then why argument 2 and 3 are to support why primary Rx undergoes your SN2 reaction. Okay, so but of course you can state all 3 arguments, just that you have to tweak it accordingly, why it supports this and why it doesn't favor that. Okay, so we're going to look at SN1 first. So SN1 is mainly for, let's write one, SN1 is mainly for tertiary Rx. Okay, so SN2 is mainly for primary Rx. Then you'll be asking, what about secondary Rx? Well, secondary Rx, it can undergo either SN1 or SN2. Now, how do you know that? Whenever they will give you, mostly they'll give you a rate equation. So if they say it's a nucleophile and it's an Rx, then of course, yeah, it's bimolecular, right? You have two reactors, so of course it could undergo SN2. But if it's rate equals to K Rx, then it is a unimolecular reaction. So it's SN1. So you have to fit and cater accordingly, and then explain accordingly. Yeah. So it really depends. Okay, so now we got that out of the way, so now we're going to explain why tertiary RX undergo SN1. So according to argument 1 is the stability of carbocation ion. So if we can recall, in alkenes I talk about the stability of carbocation ions is when undergoes the electrophilic addition. So over here it's kind of similar. Okay, before we talk about stability of carbocation ion, let us explain why in the first step of the SN1 reaction we have a breakage of the CX bond, and then it will form our bromide ions and our intermediate, which is a carbocation ion here, which is trigonoplanar. So let us explain why it is as such. Okay, so if we look at this, yeah. So we look at steric hindrance. So number one, alkyl groups are very large. Okay, so you can talk about C2H5. It can go to C3H7, and it's really a lot. It's very big. So imagine if you like so huge, then of course it will block the approach of my nucleophile over here. It's trying to attack this electron deficient carbon. So like, yeah, it's not feasible to just undergo like a backside reaction. Okay, backside attack. So then argument 2 says that electron deficient carbon. Remember our alkyl groups are electron donating, so therefore it reduces the electron deficiency of this carbon to a greater extent than if you were to look at, for example, CH3Br. Okay, so I'm going to do a direct comparison here. So number one, steric hindrance. This hydrogen atom is very small, so there's no problem with that. There's no steric hindrance. In fact, I can just straight away do my backside attack. Okay, so then if I look at electron deficiency of the carbon, hydrogen atoms are not electron donating, so of course this will still be very electron deficient. So of course the lone pair electrons will be readily attacked. Okay. Now, if we were to look at the stability of the carbocation ion, so theory 1 supports why we have to break the CX bond first. So if we break the CX bond, so that means now I'm gonna end up with a carbocation ion. Okay, so now this is my carbocation. Testing. Okay, so oops. Okay, so now if I look at my carbocation ion, okay, so like I said, the reactivity of the carbocation ion depends on how stable it is. So because it's it depends on the electron deficiency of the carbocation ion. So because I have these electron donating alkyl groups, so it reduces the electron deficiency of this carbon here to a greater extent than if I were to look at this. So if this were to form a carbocation ion intermediate, these hydrogen atoms are not electron donating, so of course this will be very electron deficient. Okay, so it disperses the positive charge to a greater extent. That's the phrase we're using here. Disperses positive charge. All right. So, but if we were to look at this, the stability, so it doesn't disperse it to a great extent, so therefore it's not very reactive if it undergo SN1 reaction. So therefore it preferably undergoes SN2. But in this, it's very stable, therefore it undergoes SN1 preferably. So there we have it. So now we will look at the energy profile diagram. So okay, before we look at the energy profile diagram, I think it's good to understand like the reaction steps. Okay, so over here, when we look at SN1, so it will form our carbocation ion intermediate first, which is trigonoplanar. Okay, as we have, I will briefly touch about it on alkene in a short while. So then our nucleophile attack, and then this is our product. It's a wedge and a dash. So it will be good to draw the wedge and the dash here. But the final product, so you should draw the wedge and the dash. Yep. Then it'll form our HBr. Okay. So what if the carbon here is actually attached to multiple different groups? So we recall about enantiomers. Enantiomers, they require a cryocarbon. Cryocarbon is when I have a carbon that's sp3 hybridized, so it forms 4 bonds and is attached to 4 different groups. So over here, it is indeed attached to 4 different groups. I have a hydrogen atom, I have a methyl group, I have an ethyl group, and now I have this NH3 coming in here, which will become NH2. So by this reaction, you must show that it can form 2 enantiomers in equal proportion. Mind the word equal proportion. So this is the mirror plane. Make sure right here, and then draw a reflection of each other. Draw the wedge in the bond as well. Wedge in the dash. So because it can form the 2 enantiomers in equal proportion, so the optical activity of this enantiomer exactly cancels out the optical activity of this other enantiomer, therefore resulting in an optically inactive mixture of products. Right. So I'm not saying that the enantiomers formed are not optically active. They are optically active because they are chirocarbon, but just that because I formed 2 enantiomers in equal proportion, so the optical activity of one enantiomer exactly cancels that of the other. So why does this happen? Because if I were to look at this, the trigonal planar, like I said, the carbocation is trigonal planar, and I have an equal probability of the nucleophile attacking the trigonal planar carbocation from above or below the plane. Okay, the word trigonal planar must come out above or below the plane, equal probability, therefore equal proportion, optically inactive. Yeah. So if we were to look at it as a whole, one part of optically inactive compound will be racemic mixture. There are also another class called meso compound, which I will not cover now. So under racemic mixture, there are actually 3 ways that we can form it. First is electrophilic addition of alkene. So if we were to look at alkenes, so it will form a carbocation intermediate. Oops. So for example, I have this, yeah. So for example, it's like that. Yeah. So then I have an equal probability of the nucleophile attacking from above or below the plane. So in this case will be Br. Oops, it's not how it's supposed to work. Hang on. So it's H and there's a CH2Br. Yeah. Okay, so I have an equal probability of my nucleophile attacking from above or below the plane. Okay, but I just know there's an electrophilic addition. Okay, but this is also the idea here. That's why it forms a racemic mixture. Then for another one, we have nucleophilic substitution of our aldehyde, which we'll talk about in carbonyl compounds. Okay, so so that's for SN1. For SN2 is a bimolecular reaction. So therefore, I have my nucleophile and my RX in one reaction. So if I draw distinctions, don't look at the rest here. So we're looking at this portion here, and it's very, very messy. Oops. We're looking at this portion here. Yeah, where I just circle out. Okay, so when we are looking at this, we'll start off with, of course, our RX, right? Then I must label this delta positive, delta negative. It is a heterolytic fission of the bond, and then my nucleophile attacking from behind. That's my backside attack. So then I will draw my transition state, TS. So I must draw a wedge and a dash. It's very, very important. Okay, you cannot miss this out. You must draw the wedge and the dash. Then these are partial bond, right? Because this is leaving, this is entering. Then I will end up with my product here. It's a primary amine and my hydrogen bromide here. So just know that it's possible for this transition state to have a charge, but this charge must be based on the nucleophile. Now we see NH3, it has no charge, so therefore we do not include the charge. Okay, but the charge is based on the nucleophile. Please note about that. And there's an inversion of the compound here. So for example, initially we started with this, and then after the whole reaction we end up with this. This is the nucleophile attached. NU. Okay, never mind. NU. So you can see there's like an inversion of like where the H was. So at first it was on the left, now it's on the right. So please note that, okay? Okay, so now I'm going to be continuing to explain the energy profile diagram. So over here, you can see for SN1 there's two humps. Why? Because there are two steps to this reaction. So firstly I'm going to have my Rx on the left as my reactant. Then I'm going to have to break my CX bond first. To break it. So then I'll get my R plus, my carboxylic ion, and my X minus because it breaks heterolytically. So therefore I have my bromide ion, for example. Then my nucleophile will start coming in and attack my electron deficient carboxylic ion. Then I'm gonna have my nucleophile, my newly substituted Rx compound. It depends. It's R nucleophile and it's my X minus. Yeah. Then we look at SN2. It's a single step reaction, so therefore I'm going to have one hump only. So I have an Rx on the left, the transition state, is where it happens, and then my R and U and my X minus. Okay, just note that for this we have 2E activation energy, and it just so happens that this middle portion here is just above the original energy level of my reactant Rx. Okay, so I think it's also good to know why NH3 become NH2. So thing about it is that I just think of it as like nitrogen likes to have its lone pair of electrons, you know. Because if I were to not consider this lone pair of electrons here, let's say once it actually achieves its octet configuration, right? But it prefers to have its lone pair electrons, so just give it. Okay, so that means my NH bond here will be breaking heterolytically, so the one pair electron goes to my nitrogen atom to give it back its lone pair electrons. Then my bromide ion that I broke earlier on, right? Then it will just attack this hydrogen atom, and then it will form HBr. Yep. So there you have it. It's kind of similar to how when you add Br to aqueous to your alkene, it forms H2O plus. But then something happens, so Br will attack the hydrogen, form HBr, and now you have your OH. So that's the reason is that. Okay, so next up I'm going to explain what's about a nucleophile, electrophile, because some people just seem confused about it. So nucleophile is when I'm electron rich. Therefore, you always see that nucleophile is its electrons and stuff. It's like lone pair electrons. Lone pair electrons they wants to eagerly donate. Electrophile, on the other hand, are electron deficient. That's why we consider the attack of, for example, this alkene here, right? It's the electrophilic addition. So over here, it's the carboxylic ions, electron deficient, therefore, yeah, the electrophile. So over here, we must always take the distinction over here. So nucleophile means I'm nucleus loving. Therefore, I want to eagerly donate my electrons, donate my lone pair of electrons, not lone electron, lone pair, which means 2 electrons. Electrophile means I am electron loving, meaning I lack electron. So I need to get my electrons, meaning I am electron deficient because I need electrons. Nucleus loving means I have so much electron, I want to give it away to nucleus, you know. Yeah, things like that. So this is the difference between the nucleophile and an electrophile. Okay, so now we'll be moving on to our Rx distinguishing test, which is the last part of Rx that we're going to cover. Okay, so now we'll be covering distinguishing tests. Okay, so what we're going to do here is that there are actually 2 reaction pathways that we can possibly conduct our reaction, our distinguishing test. Yeah. Okay, so firstly, the first pathway, there's actually a reason why we do the first and not the second. Okay, but these are two possible ways that we can do it. So the first pathway is that we're gonna first do our nucleophilic substitution. So the point of this entire distinguishing test is to um, break our bond, our CX bond, so that our halogen can come out as halide ion, and then it can form a precipitate with our Ag with our silver ions, right? Then we can form a precipitate. Then we can detect which halogen was present inside. So our first reaction is a nucleophilic substitution. So we call it's quite similar because if you can recall over here, when we convert our RX into an alcohol, we use sodium hydroxide and heat. Okay, so that's where it came from. So therefore, we are substituting it, substituting Br for OOH. So from the alcohol. Okay, but that doesn't really matter because so long as our Br come out, right? So that's nucleophilic substitution. Secondly, we need to cool and acidify with nitric acid. So why nitric acid? Because if we were to use sulfuric acid, for example, later on when we add this AgNO3, which is a soluble salt, and then it will form Ag plus and SO4 2 minus. This will give Ag2SO4, which is an insoluble salt. Insoluble, which is a white PPT, so it will give us a false positive. Alright, so yeah, so you give us the wrong conclusion, yeah. Okay, so because our AgCl is also white PPT as well, so you give us a false conclusion. So therefore we don't use sulfuric acid. We use nitric acid. Okay, then we add in aqueous silver nitrate. So the advantage of this pathway is that it allows us to see the rate of formation. Because why? If you can recall the theory, so down the group from Cl to Br to I, just examine these three halogens here. So down the group, our atomic size increases, so therefore our orbital is more diffuse orbitals because atomic size increases. So we can recall from chem bonding, because when I have more diffuse orbitals, so therefore the orbital overlap between the orbitals of carbon and bromine will be less effective. Therefore, it results in a longer bond, but more importantly, it's a weaker bond strength. Therefore, it's much more easier to break CI bond as compared to CBr and CCl. Okay, because we call I as the largest orbital and it's most diffuse, and like the orbital overlap is like the least effective, so it's the weakest bond. So then my I minus ion will start to come out first, and then when I add AgNO3, this one Ag will come out first. So whenever we add ammonia to AgCl, it will dissolve in NH3 to give us a colorless solution. But for AgBr, it will only dissolve when you add a lot of NH3, or you can use concentrated ammonia. Then for AgI, it will not dissolve. Yellow PPT will remain insoluble even when you add a lot of ammonia. So why is this so? If you can recall solubility equilibria, so whenever I add ammonia in excess, my Ag will react with ammonia to form my silver diamine complex. This is over here. This is a complex ion. Okay, so if you look at our equilibrium here, so we're using AgCl as example. So Ag plus and AgCl, it's partial dissociation. So when we form this silver diamine complex here, the concentration of our Ag plus will decrease. So then at the point that we use aqueous ammonia, our ionic product, which is Ag plus and Cl minus, is actually lower than our solubility product of our AgCl salt here. So therefore, this salt readily dissolves in water, ammonia, to give your colorless solution. But then, if you recall, trend is that down the group, for our AgX salts, down the group, our solubility product decreases, meaning it's like less and less soluble. Okay, so therefore, when we look at our cream PPT here, therefore we need to use a lot of ammonia. If not, we can use corn ammonia. Only in corn ammonia will then our AgPr decrease because dissolve, because if we just use aqueous ammonia, Ag plus, yes, it will drop to form our silver diamine complex, but it's not to a point whereby my ionic product is less than KSP, so it's not that much yet. Our ionic product, in fact, is still greater than KSP, so therefore it doesn't dissolve. But if you add but if you add a lot of ammonia, then yeah, it will my IP will become lower than KSP and it will dissolve. But for AgI, my KSP is so low that no matter how much ammonia I add, my IP will always be greater than my solubility product. So therefore, AgI is not soluble. Therefore, your PPT remain insoluble. So that's how you deduce, yeah. So other than that, we can use our alternative, which is ethanolic AgNO3. It also gives us the same results, just that it doesn't tell us about the rate of formation. Yep. So with that, we're done with our distinguishing test, and we'll be moving on to alcohol.